Right, so welcome back everyone. Okay, so before we start, I want to clear out a few things um, which I think were left ambiguous in the previous lecture. So first thing, basically we talked about ridge regression, right? And then there came a point where we discussed that, how can we determine a good value of lambda? And we discussed that, a way to do this is basically using cross-validation. And for this particular data set, we have, 1, 2, 3, 4, 5, 6, 7, 8 points. And what we can do is that, for example, if we use 2 points to regress a line, we can basically use ridge regression to find, let's say parameters of the line using those 2 points. And then basically we can test it on, 1, 2, 3, 4, 5, 6, these 6 green points, right? How well does this line perform on this validation set of these green dots of these 6 points, right? And then, so basically we can use, so this is just example of one fold, here, this is the first fold where we have these 2 points as my training set and these 6 points as my validation set. Then what we can do is that we can repeat the same procedure by saying that, okay, just take these 2 points as my training set and remaining points as my validation set. Then basically take these 2 points as my training set, the other 6 as validation set, and then we can choose last pair of points as your training set and the rest as validation set. So if you do this, you'll see that you have basically 4 pairs. So you have 8 points, which means that you can pick out 4 pairs of points. So you have like 4-fold validation here. Now, what you can do is that for each fold, let's say that you start with a particular value of lambda. Let's say that you start with a value of lambda being 0.1. And for that particular value of lambda, let's say lambda is equal to 0.1, you pick up your first fold, you regress a line, and then test that line on those 6 points, right? So you test your and find out, what is the variance. You project these 6 points onto that line, and you basically see that, how much is the sum of squared residuals, how much is the total error. Then repeat the same procedure for the same value of lambda for different fold. Let's say in the second fold, you have these 2 points as your training set, and then remaining points as your testing set. You'll get a line using these 2 points, and then you'll calculate the error on those remaining 6 points in your validation set to see how that line performs with that particular value of lambda being 0.1, right? And then repeat the same procedure in third for using other 2 points as your training set and remaining points as your validation set, and then the fourth fold as well. So now what you will get is that basically for each fold, you'll get sum of squared residuals, and then for those 4 folds, for those 4 folds, basically you just sum up those sum of squared residuals out of those 4 folds, and you'll get basically a combined total error where you have considered a particular value of lambda. For a particular value of lambda being 0.1, you'll get a total error, which is basically, addition of the sum of squared residuals of those 4 folds. And so for lambda is equal to 0.1, you'll get, some value of total error. And then you can say that, okay, let's repeat the same procedure for lambda is equal to 0.2. And, now what you'll do is that basically you'll take the same first fold and regress a line. That is, you find the parameters of the line using lambda is equal to 0.2, and then repeat the same procedure. Calculate the variance of that line or the error of that line on these 6 points. Then for lambda is equal to 0.2, repeat the same procedure for other fold. Calculate the combinatorial error on that validation set, and repeat the same procedure on third and fourth fold, and then add those 4 sum of squared residuals. right? And so for that, for the value of lambda is equal to 0.2, you'll get a combined four-fold error of some value. And then basically you keep repeating the same procedure for different values of lambda, and then you basically pick out that value of lambda, which results in the minimum combined error of all folds, right? So this is how you can find out a good value of lambda using, let's say, four-fold validation on this particular set. Okay, so this is I think what wasn't clear in the last lecture. So this completes the ridge regression discussion. Okay, so now let's come back to. Okay, so by the way, I'm following so there's this channel of Josh Timer entitled as StatQuest. You should follow this. It's a good series related to data science in general. I won't say machine learning in particular. It's really more related to data science, but it's very nicely animated. Okay, so today, I mean, the second part of this discussion is basically related to lasso regression, or let's say the L1 regularization. So far, what we have discussed is basically, imagine that if we have, let's say, 8 points, what we can do is that, let's say, we can split our data into training set and testing set. And then what we did basically is use those 2 points as my training set to find, let's say, a particular line. In this case, we are talking about linear regression, so we have no regularization penalty. And what we did is basically if you use 2 points, you will get a unique line that can process through those 2 points, resulting in a zero error in training set. But you'll see that that red line has some sort of higher or let's say high variance with respect to your validation or testing set. And then what we did is basically we use the same procedure, but here then we add basically not alongside the sum of square residuals, alongside the data fidelity term, we also added a penalizing term, which basically penalizes your high values of slope. And so this is a particular arrangement of ridge regression, and what it does is that basically it finds out that value of your parameters which has a somewhat lower slope than linear regression. But the things that blue line won't fit your training data as well as your red line. But in turn, what will happen is that even if you have compromised a little bit on your training set, your training set error will be large, but what you'll gain is that basically you'll end up having a lower error with respect to your validation set. So the idea was that if we add a sort of penalizing term, then we can penalize high value of my parameters, right? In the end, what we'll get is basically by adding a small amount of bias, we'll get a huge improvement in overall error on my testing set. Now, if instead of using square root of slope, we use the absolute value of slope, then what we'll get is basically then we'll get a lasso regression. Or let's say we will here in ridge regression we were using a squared norm or L2 norm. But if instead of using square of slope, if we just use absolute value of slope, what we'll get is basically called as L1 regularization or lasso regression. Okay, I mean this everything else is the same. The only thing is, I mean, from computational perspective, the only thing is that you'll use absolute value of slope while while penalizing your parameters. Again, so it's I mean the working is somewhat same. You'll get some sort of line. I mean, so you'll get basically some sort of line, let's say orange line, which has somewhat lower variance on your validation set, just like ridge regression. But there's a little bit of difference. I mean, if you from computational perspective, it doesn't seem much of a difference. We are only using absolute norm instead of L2 norm, but we will see that there are certain cases where Lasso regression can help compared with ridge regression. So in summary, ridge regression and Lasso regression, they look quite similar. In ridge regression, you just have to penalize the squared norm. In Lasso regression, you just have to penalize the absolute norm. And if you look at these two lines, the blue line is the result of ridge regression, the orange line is the result of Lasso regression for a particular value of lambda, that is. You'll see that both. I mean, so Lasso regression is somewhat in between, linear regression and squared norm. So L1 norm basically lies. It does. I mean, it has some properties of linear regression, but I mean, it had the orange line basically has higher value of slope than blue line, right? So Lasso regression, well, it ends up being somewhat in between your L2 norm and your linear regression. So it hasn't got as low slope as ridge regression model, but I mean it's somewhat close, right? But it again, so in terms of training error, you have some sort of training error, but the good thing is that you're also somewhat closer to your linear regression model. But we'll see that how these two lines, I mean, here it doesn't seem much of a difference, but we'll see the cases, especially where if we have some useless variables which we can discard, then Lasso regression will help compared with ridge regression. Okay. Okay, so I mean, so let's say that, I mean, so now we are going to see the difference between Lasso and ridge regression. Okay, so let's say that we start by taking lambda equal to 0, and if we see that lambda is equal to 0, then linear for lambda is equal to 0, I mean, if lambda is 0, then the penalty doesn't make sense. You'll end up arriving at the same solution as your linear regression. So for lambda is equal to 0, linear regression is equal to Lasso regression is equal to ridge regression. So all of these three models are equivalent for lambda is equal to 0. But let's say that instead of using the squared norm, we use absolute norm. Now, if we start using absolute norm, then you'll see that as we increase this value of lambda, we'll get more horizontal, or let's say the slope will start getting towards 0. And for some value of lambda, it will be exactly 0. We'll see how that works. But let's say for the particular value of lambda being 10,000, we'll get this horizontal slope, which is like m is equal to 0, right? But then we will see that if we had used ridge regression, then even for such a higher value of lambda, we will not get exactly 0. We'll get some value of slope, which which will be small, but it will be, let's say, 0.00001. But once again, it won't be 0. But using lasso regression, we'll see that for a particular value of lambda, how can we arrive at, how can we basically remove a particular variable? Here slope is equal to 0 means that size, is not dependent upon weight. Whatever you'll choose the weight, it will give you the same size. So lambda, so slope is equal to 0 means that, you have basically neglected out some feature of your training data. Okay, and this basically means that, let's say that if you have, let's say, four variables, you have four features and they are related, and but with these five parameters, y-intercept, slope, die difference, astrological offset, and a speed scalar. So let's say that we have size of a particular animal. Let's say we are talking about a swallow. Swallow is sort of a bird, and we say that, okay, the size of the swallow is dependent upon its weight, it's dependent upon the diet that swallow has, and it's somehow also dependent upon astrological sign, which doesn't make sense, by the way, but this is just a mock-up example showing that, if we can have we can have an equation where, let's say some variable is not dependent upon a particular on some other variable, right? And so we are saying, for the time being, we are saying that, the size of a swallow is dependent upon its astrological sign with some factor, let's, and a size of a swallow is also dependent upon weight with some factors, which is like the slope, and the size of the swallow is also dependent upon high fat diet that the swallow has with respect to some factor, and then it also depends upon airspeed of the swallow, which again doesn't make much sense. So basically what should happen is that we should have high values of slope and diet difference, because weight and high fat diet contributes more in determining the size of the animal compared with astrological sign and the airspeed, or let's say how fast the swallow flies, and in which month the swallow is born. These two variables doesn't, I mean, they don't seem to have such a good relationship with the size of the animal. But let's say we say that, okay, this is how my variables are related, and technically what should happen is that I should get a higher value of slope and diet difference and a lower value of astrological offset and airspeed scalar. So basically I have formulated this problem in such a way that you know uh, I'm conceiving this beforehand, that these airspeed scalar and astrological offset should be zero. There should be no contribution of this sign and airspeed of swallow variables with this size. And for this, we'll see that if we use lasso regression, then for a particular value of lambda, we can have these two parameters go to zero quite quickly compared with ridge regression. So penalty, what will happen is that if we use in terms of penalty, if we use ridge regression model, then alongside data fidelity term, this will be the penalizing term that we will have. Lambda scaled by the sum of squared norms of my parameters, right? So these four parameters, along with y-intercept, these are the five parameters that I have to find. And while finding each of these parameters, I will say that, I should also be looking at this factor and minimize this alongside my data fidelity term. Now, okay, and if we make this lambda go large, what will happen is that we will end up, technically what will happen is that we'll end up a higher value of slope and diet difference at a very low values of astrological offset and airspeed scalar. but these the values of airspeed and astrological offset will be low, but it won't be zero. In contrast, if we use these, um, if we don't use squared norm and if we just use absolute values, then we will see that these two scalars, astrological offset and airspeed scalar, will exactly go to zero. They will all for a particular value. If we set a good value of lambda, then we will see that these two parameters will go to zero, and what we will left, or what we will be left with is a simple equation which says that size of animal is only dependent upon weight and fat and high fat diet. So I mean, I will discuss this in depth in next half an hour. How will this happen? But I'm just throwing it beforehand that if we have some relationship of variables where we have let's say some variables which are, let's say, noisy variables, or which are not dependent, or which have a very low dependency upon output, then what I should do is that basically I should use lasso regression instead of ridge regression, just so that these two parameters of astrological offset and airspeed scalar go exactly to zero. Now I'm going to explain what does this mean visually, but just to throw it beforehand that if you have a model where we have lots of variables, some of them are useless and some of them are useful, then you should use loss regression instead of ridge regression. Uh, okay, and so how does this work? So imagine that we have let's say so for timing we are only interested in one variable. So we are saying that height is related to weight, which means that height is equal to y-intercept plus slope multiplied by weight. Or so it's a simple univariate linear model. And when I say that height is equal to y-intercept plus slope multiplied by weight, this means that I have to find out the value of slope, which results in a good fit in some sense. Okay, and let's say, so we'll start with simple linear regression model. If I say that this is the line, this blue line represents my model, then technically what will happen is that I should compare this line with other lines and see that how does this line perform with other lines. So what I can do is that basically I can project all of my points on that line and then say that, okay, what is this minus this whole square plus this minus this whole square plus this minus this whole square plus this minus this whole square. Simple data fidelity term. I'm measuring how good my projection is with respect to actual points. If I have four mouse, if I have four mice, I want to see that how good are my predictions for each mouse in combinatorial sense. So this is what we call as sum of squared residuals. And for that particular value of zero, basically if I add this minus this whole square plus this minus this whole square plus this minus this whole square plus this minus this whole square, what I'll get is that, I'll get a value of 10, let's say, hypothetically speaking. And then I can play this game, or, again and again, I keep changing this slope. Let's say I increase this slope somewhat, and so let's say that we increase this value of slope, and let's say this value of slope is 0.2. And then I do the same procedure, see how my projections perform, calculate the sum of squared residuals and plot it over here. So for this value of 0.2, this minus this whole square, this minus this whole square, this minus this whole square plus this minus this whole square gives me value of around 4. And likewise, if I keep repeating this, let's say I increase the value of slope once again, And I once again plot the value of sum of squared residuals, and then I keep increasing and plot the value, the, the error again. This is equivalent to plotting. So this is, you'll end up having a parabolic curve, right? And this parabolic comes, the parabolic curve comes from the fact that what we are plotting is actually the sum of squared residuals, and since we are using this second order polynomial like function, we are getting this polynomial like curve, parabolic curve. So I mean, for this, intercept is for the time being constant. We are only saying that for some value of intercept, which is like you know this value over here, just keep changing the slope, and you have your actual data, and you have your particular value of slope. You know your weight, and you from this, whatever is inside this bracket, you'll get your predictions, and you actually uh, basically calculate the difference between your observed values and predictions, and you squared it over all points, and then you basically just plotted out this line. Now, this means that the best fitting line in terms of linear regression is basically, the minimum point of this slope. So for, let's say, slope is equal to 0.44 or 0.42, this is the best line that linear regression says that we can have. Okay, so so slope is equal to 0.45 is the best line that we can get from linear regression. Okay, and so let's say that we add this penalty of ridge regression. Now, if we add this penalty of ridge regression, what we are saying is that, whenever you are calculating error, you should also calculate this term and then add this. So let's say if we have lambda is equal to 0. Now, lambda is equal to 0 means that, we are neglecting this term. So if lambda is equal to 0, basically you'll get the same curve over here. If you for lambda is equal to 0, if you keep changing your slope, you'll get the same error as you are getting in the case of linear regression. Because for lambda is equal to 0, we are totally neglecting this penalizing term, right? And then what if we do is, let's say that we say that, okay, what if I choose lambda is equal to 10? Okay, now what you have to do is basically, let's say, repeat the same procedure all over again for lambda is equal to 10. So let's say you start with this horizontal line which has slope of 0, right? Now for this slope, you once again calculate the error. Your error will be, again, so the value, and the value will be the same. But now you also have to add this second term, which says that, you should take out your, you should calculate the error of those 4 points and add, you know, lambda multiplied by slope square, whatever that is. Now lambda is equal to 10, but now for this particular line, we have the slope is equal to 0, right? So for lambda is equal to 10, but since slope is 0, you'll get the same point, as you'll get on the blue curve, right? So now, so repeating the same procedure, we increase our slope, and let's say we increase our slope to, let's say lambda is equal to 0.2. Now, for lambda is equal to 0.2, what you'll get is basically, you'll get your error, but then you'll also have to add this penalizing term, which says that, you should multiply lambda with, 0.2 square, which is your particular value of slope of this line. And if you add this 10 multiplied by 0.2 square, you'll get 0.4, and you'll get some error. I mean, it doesn't, I mean, it seems that it is on this line, but it's not necessary, right? it's zero point 0.4. The term is, we have added 0.4 onto my sum of squared residuals. Now, if we increase the value of slope to 0.4, we will see that 10 multiplied by 0.4 square gives me 1.6. And if I add this error, for this value of 0 0.4, I'll get this point. And likewise, we start in we start increasing our slope, and we basically plot this curve, which will tell me that for lambda is equal to 10, this is the curve that you are getting, or this is how your slope changes your overall error for lambda is equal to 10. Now, if you use the value of lambda is equal to 10, you'll see that the minimum value that this function has is a little bit left compared with my linear regression model. So linear regression model was saying that 0.45 is my optimal solution, but here I can see that 0.39 is my optimal solution using lambda is equal to 10. Now, so if let's say that we increase this value of lambda to lambda is equal to 20. If you repeat the same procedure, you start you start by choosing a lower value of your slope, and then you start increasing slope little by a little bit. I mean, how much your slope should increase, this we will discuss. I mean, it will depend upon the gradient, and we'll see that what should be the optimal size of uh, of my gradient, and how should I increase my value of slope. But for the time being, if we just, let's say, keep increasing slope by some fixed value, we'll see that for lambda is equal to 20, we'll get this curve. But then if we see the minimum of line of this lambda is equal to 20 curve, we'll see that this curve approaches minimum at lambda, or at m is equal to, or slope is equal to 0.3, right? So what this means is that if I keep increasing my lambda, the slope gets asymptotically close to zero, but not exactly zero. If for lambda is equal to 40, those 4 points will tell me that this is the optimal line that you have, which has the slope of, let's say, 0.2. But if I chose lambda is equal to 10, then it says that, okay, you should use lambda m is equal to 0.39, or let's say closer to 0.4. So as I keep increasing my lambda, uh, the overall effect will be that I'll get lower value of slope as my optimal solution. Right, so this is the net effect of ridge regression. But okay, so and now let's repeat the same procedure with absolute penalty, right? Or let's say the L1 norm, or what we call as Lasso regression. If we use the same procedure, and let's say for lambda is equal to 0, we'll get the same line as my linear regression curve, right? And then let's say that we'll, for lambda is equal to 10, if I repeat the same procedure, start with some value of lambda, start with some value of m, and then I start increasing it, I'll get this curve. But here you'll see somewhat elbow like bent, or let's say a kinky structure over here, which basically, and this kink will be more visible if you start increasing your lambda. And for lambda is equal to 20, you'll see that this kink will be more visible. Now, once again, the interpretation is quite similar. For lambda is equal to 0, I'm saying that 0.45 is my optimal solution. For lambda is equal to 10, this minimum value of this orange line appears over here. So which means that 0.35 is my optimal solution. For lambda is equal to 20, the minimum value is around 0.2, which means that my optimal solution is at m is equal to 0.2. And if I keep increasing lambda, for lambda is equal to 40, what you'll get is basically this sort of a curve. And this curve will tell you that, the minimum is at slope is equal to 0. Your best optimal solution for lambda is equal to 40 is that if you choose m is equal to 0, which basically means that if you choose this line, which in turn means that your height should not be dependent upon your weight. Whatever your weight chooses, your height will remain same. So the the overall effect of this of using this absolute penalty is that for a particular value of lambda, you'll get closer to 0, or let's say you shrink your parameter very quickly to 0 compared with ridge regression. So in terms of if we were using ridge regression, then even if we had chosen this high value of 400 for lambda is equal to 400, we will see that we would not be arriving at 0. We will, I mean, even for lambda is equal to 400, we see that the slope is greater than 0. But if we had used Lasso regression, what will happen is that you'll get 0 for lambda is equal to 40, and for here you'll see that for lambda is equal to 40, it was saying that your solution should be m is equal to 0.2, or that that line should have a slope of 0.2. But here for lambda is equal to 40, I'm getting a slope of 0, which basically says that which basically means that I should totally neglect my variable in calculation of my output, which means that output is not dependent at all on my on my uh, on my variable that is scaled by this slope, right? So this is technically what happens if you use lasso regression compared with ridge regression. I mean, you'll shrink your parameters quickly towards 0 by using a lower value of lambda compared with ridge regression, right? So what this means, so this is the visual explanation of what we talked about earlier. If we have like if we have some parameters, if we have equation which is related to 4 parameters, where only 2 parameters are useful and the rest of 2 are useless, then I want these 2 parameters of astrological offset and airspeed scalar go quickly towards 0, and that can only be achieved using lasso regression, not with the ridge regression. Uh, okay, so I mean, in technically, you can also look at it over here. So for example, if you have a variable y which is highly dependent upon x1, which is very, let's say, which is not dependent too much on x2, it's dependent somewhat on n3, or on x3. It's not dependent at all with respect to x4, and likewise it is also not dependent on x5, but it is highly dependent on x2, and we have some intercept as well. Okay, so let's say that this is the model that ridge regression gives you, right? So the ridge regression gives you intercept of this and 1, 2, 3, 4, 5, 6 parameters. So ridge regression gives you 7 parameters, 1, 2, 3, 4, 5, 6, 7. But had you used lasso regression, what you would have achieved is basically it will shrink this factor towards 0. It will also shrink this 0.0009 to 0. It will also shrink to this factor to 0. And what you'll end up is basically 1, 2, 3, and 4 parameters. So Lasso regression is more useful here in this case because it will quickly shrink your parameters of which are related to your useless variables uh, closer quickly to zero, right? And okay, so this is advantage of Lasso regression versus ridge regression. Okay, now there is one thing that still remains, and this is basically okay. We saw that we have a closed form solution uh, of uh, of linear regression, and we also have like this, right? So we saw that we have let's say a closed form solution of linear regression, and then we also discussed approximate solution of linear regression. Now if so, the same goes for ridge regression as well, and for Lasso regression as well. So for ridge regression, okay, so this is the closed form solution of ridge regression. So I mean, so imagine that this factor goes to zero. This is like for the timing, just forget this factor. So X transpose X whole inverse multiplied by X transpose Y, like this is exactly equivalent of what we saw over here. X transpose X. So imagine that, I mean, here we are talking about A and B, but, let's say that you have X over here instead of A, and, Y over here instead of B. So X transpose X whole inverse multiplied by X transpose Y, this is the closed form solution of linear regression, right? So, I mean, if you just ignore this term, what you'll get is basically the closed form solution of linear regression. And if you just add this term, which is lambda multiplied by identity matrix, what you'll get is basically a closed form solution of ridge regression. Uh, I mean, I don't have time to derivate this right now, but you can. I'll send this document. So basically, if you just basically put your derivatives equal to zero, you'll end up, with this equation over here. So this is the only difference between the closed form solution of my linear regression with my ridge regression. Lambda is over here, so lambda plays a role in determining my optimal solution. So what this means is that instead of using a gradient-based solution, you can also use this closed form solution in order to, find out the parameters, in linear algebraic sense. Okay. So now comes the closed form solution of your Lasso regression. I mean, so here, I mean, there's this assumption of orthonormal variables. I mean, so this is only applicable. So, this closed form solution is only applicable if you have such variables which are, orthonormal, which means that, if you, let's say that we are talking about a house and, it has, let's say, 3 or 4 features. If you and let's say we have 10 houses and let's say 3 features, so we have this matrix of 10 rows and 3 columns. If you calculate the dot product of those features in between themselves, then the dot product should be equal to 0. That is to say that first column should be orthonormal to the second column, or let's say orthogonal to second column. And likewise, if you calculate the dot product of first column with third column, it should also be 0. But then if you calculate the dot product of first column with itself, then it should be equal to 1. So this means that your column vectors should be orthonormal, which means that the dot product of those 10 numbers in first column with itself should be 1, and with any other column, the dot product should be equal to 0. So those, if that condition is satisfied, which means that, if you have 10 houses and you have 3 parameters, then if this condition satisfies, then this means that your features are orthonormal. Only then we can have a closed form solution in the form of this, which is basically the same question, the same closed form solution of ordinary least squares multiplied by this term. And I mean, so this term is basically, and I mean, so n comes over here because we are saying that, average out the squared error. But if you just forget about this n and say that, this n is 1, then, you can also say that, this is simply lambda over ordinary least squares norm, right? So this ordinary least squares solution is basically this one. So it appears over here and it appears over here as well. And then you have norm of this, and then simply multiply by the maximum of this. So I mean, we have a closed form solution of this of Lasso regression as well. So this is only, so right now I'm talking about Lasso regression. So we have the closed form solution of Lasso regression as well available, but then there's this assumption that features should be orthonormal. If they are not, then you can only use a gradient based approximate solution, right? And so we'll discuss this in a minute as well. So just to summarize, we can have closed form solution of linear regression, we can have closed form solution of ridge regression, and we can have a closed form solution of Lasso regression. I mean, constraint on some assumptions. But now let's discuss, the ordinary least square solution of of all of these. So right, we have discussed, so with no regularization, we have simple linear regression model. And here, I mean, the loss on a particular, let's say, cost of a particular point is pretty simple. Just calculate the square difference between your actual versus predicted points. But here in L1 regularization, we are saying that, okay, add a penalty with respect to absolute value of this W, right? And in ridge regression, we are saying that, okay, while you calculate this error, you should also add the squared norm of this W with respect to this lambda, right? So here there's no penalty, here there's lambda multiplied by absolute value, and here we have this lambda multiplied by square value. The data fidelity term on the left remains same in all three. In linear regression, we only have this data fidelity term. Here we have this data fidelity term with this term, and here, in ridge regression, we have this data fidelity term with squared norm of my weights. Now, so technically what should happen is that, I should calculate the derivative of this loss function with respect to W and B. So I mean, what we are going to do is basically, if we are using an approximate solution, then we should I mean, we start with a particular guess of W, and let's say start with W is equal to 0, or let's say, I mean, so here we saw that so here for every curve, while for every curve, we basically started with some initial guess of W. So we started with W is equal to 0, or let's say slope is equal to 0, right? And then we basically say that, okay, this is the loss with it, or at that point, at that slope, at the value of slope is equal to 0. And then we said that, okay, let's increase the slope from 0 to, let's say, 0.2. But then the thing is that how how should we say that, why not increase the slope from 0 to zero point 0.1, or let's say 0.05? Why increase the slope from 0 to zero point 0.2? How can we determine this step size of, let's say, 0.2? You know, we said that, start with 0, calculate the loss, then, jump to this 0.2 and calculate the loss, and then jump to this 0.4 and then calculate the loss. But what how we arrived at this particular way of suggesting that, you should add 0.2, not, let's say, 0.1 to the step size, right? So this is my W new and this is my W old. So we started with 0 and then we jumped to 0.2. And right now what we are discussing is that how can we arrive from 0 to, zero point 0.2? And the only way of arriving is using linear, using gradient descent, is basically, start with some value and then basically move towards negative side of this gradient. uh, and this gradient basically measures how my loss function is changing with respect to my particular value of W, let's say. So we start with 0 and then we basically have to calculate this function, and this function, what we actually calculated is, um, so we actually calculated this beforehand, while we were discussing it. So we said that, the derivative of the function with respect to slope is minus 2xi, multiplied with this. So this is actually the same that we are discussing right now. You know, so this is actually the same. So, those two terms are basically equivalent. So this is how you should be updating your slope. Start with a particular value and then, using a particular step size, add this much of factor. Now this is simple linear regression, right? But if we use L1 penalization, or let's say lasso regression, well, then if you have this function, let's say, and you calculate the derivative of this function with respect to W, then what you'll get is that, 2 multiplied by this multiplied by x plus, lambda multiplied by this. And now the problem is that, what is the derivative of lambda, dw with respect to W? So it will depend. So since this is the absolute sign, then it depends that whether W is positive or negative, so d by dx of absolute x is 1 if x is equal to 0, and it's minus 1 if x is negative, right? So when you basically calculate the partial derivative of this loss with respect to your W, what you'll get is basically this factor. So for linear regression, we only had this term, but for ridge regression, the derivative also contains this term, and this term is basically, lambda multiplied by this. This will be positive if W is greater than 0, and this will be negative. The derivative, if W is negative, then the derivative will be negative. So what we are saying is that if W is greater than 0, then we have plus lambda. Otherwise, we have minus lambda over here. So this is how you will update your weights. If your initial value of weight is negative, then you should use this equation. Otherwise, if your initial value is positive, then you should use, this equation to get your new value of slope from previous one. And likewise, in terms of L2 regression, once again, we have this term. If you calculate the loss of this with respect to W, 2 comes over here. So we have 2 lambda W multiplied by derivative of, W. So, and derivative of W is 1. So we have 2 lambda W over here. So this is the derivative of basically this loss function with respect to my slope. And right now I'm only talking about, how to update slope, but, if you see that how to update intercept, the intercept will be updated in the same way as my slope is, but the only difference is, the difference between regularization, the difference between, linear regression and lasso regression and ridge regression is how to update parameters that are dependent upon that are scaled by my measurements. For y-intercept, there won't be any change. Since we are saying that, okay, what will be the derivative of this with respect to b? This is the y-intercept. I also want to find the parameter of b. So here it doesn't matter. So the derivative of this loss function with respect to b will be the same here. It will be the same over here, and it will be the same over here, because the only difference is this term, but here this term does not include b, and therefore the derivative of L with respect to b is constant for linear regression. It is the same for this one. It is the same for ridge regression as well. Because this penalizing term doesn't have b. So the way of updating my intercept, which is b in this case, is the same in all three models. Okay, so this is how we will update slopes in linear regression versus lasso regression versus ridge regression. And so, I mean, if you look closely, 2x multiplied by wx plus b minus y, this term is the same over here. It's the same term over here, and it's the same term over here as well, right? So let's say that we substitute this term with, h. We say that this term is equal to h. So because, this term is constant in all three models, so we don't want to, we will see that we say that, this term does not affect the comparison of my three models. So if we substitute this term by h, so we have w minus, step size multiplied by h. Or let's just, I mean, so for the timing, we assume that step size is 1. So we have this term, which basically says that, take initial value of slope. And if you are using simple linear regression, then, subtract this and you'll get your new value of slope. Now for lasso regression, we are saying that, okay, not only subtract this, but if your weight is greater than 0, you should also subtract lambda. And the net effect is that if your weight is positive, then you'll get closer to 0. But if your weight is negative, if your slope is negative, then you should add lambda, which means that negative values should increase and positive values should decrease. So this is how we said that if we choose a particular value of lambda, then we will arrive quickly towards 0 using L1 regression compared with L2 normalization. So compared with L2 regularization. So in terms of L2 regularization, you see that the slope is updated relative to the weight of the slope itself. So if the slope is, let's say, if the slope is, let's say, 0.1, or the slope is very low, it doesn't matter how much large value of lambda you have, that since the step size is, let's say, corresponding to your weight, your weight will be, you'll move slowly towards 0. But here, the the step towards 0 is only dependent upon lambda. Here it is also dependent upon w. So that is why you won't go quickly to towards w nu is equal to 0 here compared with L1 regularization, because here we are using a constant lambda step size, but here, we are saying that, okay, you should use 2 times of w uh, alongside lambda as well. So you should scale your lambda with 2 times w. And that is the reason, that you won't arrive quickly towards 0. Um, okay, so I think I've covered almost everything. So yeah, so the major difference is that here we are dependent upon sine of w. The only thing that that depends, that basically governs how quickly I should move towards zero is the sign of the weight. But here actually, the weight itself is also included in my movement. Right, so that's it for today. So this completes the lasso regression comparison with ridge regression. Thank you.